Hello everyone, I'm Aerospace Engineer Mohammed Mershazar. Today I'm going to give you a presentation about enhancing forensics analysis with autonomous UAV deployment for aerial investigation. The present study aims to develop a unified sensor and communication system on quad-rotor drone architecture with full autonomy as a scalable 4G LTE IoT-based platform that includes path planning, artificial intelligence, and computer vision algorithms to collect atmospheric data with high maneuverability. This design engine boosts an infrastructure to improve the system by making a positive contribution to future studies. This will pave the way for future atmospheric measurement based on material system studies. And we will discuss this set under 5 main headings. First, what is unmanned aerial vehicle? An unmanned aerial vehicle, commonly known as a drone, is an aircraft without any human pilot, crew, or passengers on board. Flight check and the system methods. The figure shows together with the block diagram how to quadcopter control system controls before, during, and after the flight, monitor and collect atmospheric data. In this context, in order to prevent possible malfunctions and the accidents before the flight, it is check all the system after the controls. Is that time there is no problem, the engines of the drone are started and the mission flight is started. After the start of the mission flight, the drone is calibrated to ensure the true data. During the mission, it is collect the real-time data that include atmospheric parameters. After collecting the atmospheric data determined for the target area, the mission flight is completed by returning to landing strip. Overall system design. The entire avionics system architecture of the rotary wing unmanned aerial vehicle with a quad-X array with 4 rotors, which can provide autonomous and encrypted communication, make atmospheric measurements, and maneuver using hardware and software features without assistance is designed. Flight control software and various external sensors are needed to perform atmospheric measurements. With Pixar Orange Cube on flight control board, RFT telemetry module, WASP LiDAR sensor, MATEC module, MATEC GPS module are used. For Sun Sky, motors are used to carry these systems on the quadcopter and generate thrust. In order to give the best performance with the engine T-motor, electric speed controller, and the double-bladed carbon fiber propeller are used, considering its compatibility with the system and its cost. The power supply required by the flight control, mission control unit, and the power propulsion system of the power management system is used. Distributed power needed by the equipment on the drone is provided by lithium polymer battery. For BVLOS remote operations based on the real-time 4G LTE connection XP station kit, which a plug-and-play hardware that can reliably transfer drone data and the video to ground station or IoT monitoring and the control station with automatically reconnected to the cloud connectivity even if the network is lost. Easy use. In order to monitor the vehicle during the flight and the imaging system, the XP-Link 4G LTE module, which provides IoT communication and the control connected to the flight control system, has an HDMI interface that offers 8 megapixel 160-degree ultra-wide angle and the full HD video shooting quality and the lowest delay in order to follow the drone during the atmospheric flight. In order for the sensor module to fulfill its task, Atmega 52560, which has the 8 kilobyte SRAM, 4 kilobyte EEPROM, 256 kilobyte flash memory, 8-bit, and the 16 megahertz speed and the allows working on the any platform is used. The voltage regulated using the microcontroller operates in the range of the 6 to 9 volt DC. In addition to M8Q WASP LiDAR on the Pixar Cube Orange flight control board, PM2.5 or PM10, dust and air quality sensor, ozone sensor, infrared carbon dioxide sensor, VOC sensor, CO sensor, NO2, H2, NH3, CH4 sensor, loudness sensor, and the digital UV index IR visible light sensor are also used. Route determination. The dimensions of the test area are reported to the drone at the beginning of the flight and they remain constant throughout the flight. The drone needs to scan this area efficiently and quickly and the detector test results. The drone has an XP-cam camera, the operating altitude range of this camera, the angle of the view, the placement angle of the pitch axis, the drone are specified in scenario variables. While making this sharing attention should be paid to the efficient scanning of the entire areas except for the prohibited areas and the high-rise buildings. Field scanning. When it reaches the duty area for area scanning, the area to be scanned is divided into sections considering the camera field of view to the drone and the coverage areas on the base station. The segments are numbered from the right to left, starting at 1 according to the direction the drone came into the area. The drone scans to the first division and transmits the sensor data it is detected to the IoT and the ground platform. Scanning is done on a line-based basis since the task area is quite wide. In these circumstances, it is more effective to use the line-based search method. The start of the scanning is shown in figure A, and the movement of the drone that is completed is part of the figure B. One of the purposes of using this method is keep the areas close to each other and increase the information sharing between the areas from which atmospheric data is taken. By dividing the area into sections, route crossing and the collision risk are reduced. Main solving a function, the main solving library was used in the solver function to determine routes. Correct the GPS zone. The GPS noise flag becomes true when the drone continues to flight in the mission area in cases where the GPS signal is cut off and the route is follows or when unknown location is entered. When this flag is true, is understood that the GPS signal is corrupted and the backup GPS module is activated. The task of this module is to prevent the drone from getting the loss, keeping the yaw angles constant. When the GPS signal improves, the skin module is reactivated and the backup GPS module is disabled. In addition, there is no distortion in the heading angle when in the corrupted GPS region. The drone can resume the flight when the distortion in a GPS signal is corrected. Collision avoidance and no-fly zone. There may be stationary or moving objects in mission areas to be avoided. Stationary objects are excluded from the areas that can be flown regardless of height. When the drone comes to these regions, it creates the shortest route to reach the target point as shown in the figure. Red areas are areas where flying is prohibited or where tall buildings are located. When approaching these areas, the altitude of the drone can also be seen. Avoidance of moving object is done by changing course by the certain amount. When the drone encounters other objects where the routes intersect, it performs predetermined avoidance maneuvers. These are up and down depending on the height and size intersecting vehicles. Conclusion. As a new platform for measuring atmospheric parameters in situ, and combined sensor and communication system has been developed in detail using the autonomous quadcopter application fully enabled with fully autonomy IoT. In the design of the system, the sensors, microcontrollers, and PCBs required for the avionics system were brought into the complete package, and each sensor was connected within the scope of the requirements, and the three platforms were created, namely air, ground, and IoT. Telemetry systems to provide real data exchange with the drone flight computers and the 4G LTE module have been tested to operate the desired sensor. In addition, thanks to the proposed avionics architecture, mission-critical data obtained from the sensors is transferred to the cloud, ensuring the easy tracking and the control over the software platform regardless of location. FutureWorks, we would like to verify the durability and the long-term operational stability of the proposed system for unmanned vehicles, studies that can provide high-resolution spatial-temporal sampling that is possible for future studies. We would also like to work on developing several sets of our proposed system with simultaneous flight measurements to improve and the spatial and temporal resolution of our smaller, lighter, high precision, and remote operated vehicle for new technologies in fields such as chemistry, physics, and information technology. Thank you for listening to me. If you have any question, please let me know.